this exercise and the next several exercises are focused on applications of the singular value decomposition for low rank approximations and basically working with real images. Now, this is a concept that I introduced you to in the previous chapter, in chapter 14. There, we were computing low rank approximations of just these smoothed random noise images. And here we are going to repeat basically the same code, or certainly the same concept, but using a different picture. So here I have the URL of a picture. It's a picture of Stravinsky. It's actually a drawing, not a picture, drawn by Picasso. Okay, so for this first exercise in this series, exercise 10, what I want you to do is import this image. Again, here's the URL. You can also just look at the code solution online and copy and paste the importing code. Now, this image is a 3D matrix. So it is rows by columns by color channels. So this third dimension here is RGB. But working through these examples, these illustrations in 3 dimensions is not impossible. It's a little bit tricky. You've worked with 3D images before with convolution and image filtering. So you can refer back to that chapter where I discuss the different ways of working with and applying these kinds of multivariate linear algebra based analyses on 3D color images. But for now, I recommend, just for convenience, for getting a handle on the methods and the math and the code, just convert the image to grayscale. That's just going to make your life easier for the next several exercises. Okay, so you want to import this image and then basically produce a picture that looks like this. So what are we looking at? This is exactly the same idea as we used in the previous chapter. So that was exercise 5 in chapter 14. So what I recommend doing here is going back to your code solution for exercise in chapter 14, exercise number 5, copy that code and paste it into your code for this chapter, and then just modify whatever you need to for this image. So here you see the picture of Stravinsky, this line drawing. This is the scree plot. Here are the first 4 individual layers, and here are the summed layers. So you can already see this doesn't really look like a great reconstruction of the original image. Quite a different conclusion from that which we drew in the previous chapter when we had the kind of small, just smooth noise image. So I'm going to talk about this more in the code part of this video. So here is the URL, and I'm using this skimage.io to read in this image and then convert it into grayscale. Okay, so then we just make a picture of this. It's a beautiful picture. So here is the picture. It's a line drawing picture of Stravinsky by Picasso. Very interesting story behind this picture, which you can read about online if you are curious. And so I had to, so apparently that Wikipedia link wasn't working just now. And so I replaced it with this image here at this URL, but I will fix this and update the code as necessary. This picture is actually already 2-dimensional. So I also just commented out this line. Anyway, I'll make sure that this URL is valid in the code on GitHub. Okay, so let us proceed. Here I take the singular value decomposition of this image. Here I'm just creating a sigma matrix and populating the diagonal elements with the singular values. Okay, and one thing I forgot to point out here is the matrix size and the rank. So this is a full rank matrix. It is 640 by 430. And it is a full column rank matrix. So it has its maximum possible rank given its size. Okay, so let's see. Here we can see the scree plot. And just like what I showed in the book figure, you can see the first component is huge. Now we could convert this to percent variance accounted for, but that's not really necessary here. So you see the first component is huge. All the later components are almost looks like a flat line, but it's not going to be flat. And now, we'll explore what this component means in a moment. But one thing you can see is that the picture is positive value. This matrix is positive valued. There aren't any negative pixel intensity values in this image. So there's a mean offset of all of the numerical values across all the pixels here. Okay, so let's see. Here I'm just creating some of these other images from the SVD. Here I'm creating the individual layers. So here, this is again just like the code from the previous chapter. I'm computing the outer product between each column of U and the corresponding row in V transpose and scaling that up by the corresponding sigma value or the singular value. Okay, so then I show an image of that rank 1 matrix and then the sum over all of the rank 1 matrices so far, so the cumulative sum. So the original Stravinsky picture, the scree plot, here you see the first 4 layers. Now this already is really different from the example in the previous chapter, right? In the example in the previous chapter, you could actually look at these individual layers and kind of see what in the image they were representing. And that's really not possible here. I mean, this just looks like a grid, right? These just look like grids. Here, even when we look at the sum over the first 4 layers, if I showed you this picture, you would not guess that this corresponds to the Stravinsky picture. It's like nothing like it. You just see the text at the bottom, so that's kind of coming out. And otherwise, I think the message here is it is not possible or not feasible to do a rank 4 compression of these data.